Welcome to the channel Engineering Knowledge, a basic key to research in wireless communication channel deals with derivation of outage probability. What is outage probability, how it can be analyzed over wireless fading channel. This all we are going to discuss in this lecture. Please do watch the video till end to understand the basic concepts of outage probability and how we can use the concept of random variables in wireless communication channel to derive an expression of outage probability. Let's get started. So in this lecture, we will discuss the basic concept of outage probability and how analysis over fading channels can be done. In the previous lecture, we have discussed several times about the multipath fading. You can check my previous lectures for the same. If there is a flat fading channel, then the symbol xp of t minus tau I, where tau I is the delay, can be approximated as xp of t, and the received symbol yp of t can be written as multiplication with the channel with the narrowband signal. This approximation is called narrowband signal. And the complex wireless channel is given as a sum of all the multipath components, where h is simply ai e raised to the power j 2 pi fc tau I. What are these components? First of all, fc stands for the carrier frequency. Tau I is the delay at which each multipath component is received at the receiver, and ai is the amplitude attenuation that each component suffers. This is amplitude. So in order to model this narrowband channel, we use statistical models like the relay fading channels, shift model for Nakagami, and fading channel can be used. For severe fading, we can use Rician model with line of sight, or a K distribution also can be used. So, and there are multiple other models that can be used statistically to represent the channel that represents the multipath fading of a wireless communication system. Now, how does we represent this wireless systems? So there is a wireless user. It wants to communicate, suppose, to the BTS. This is uplink I am discussing here. This is BTS, the uplink. This transmission takes place in the presence of H. H is the fading. So the signal is attenuated and delayed due to multipath propagation. And apart from that, there is also an omnipresent additive white Gaussian noise. So how do we model? Suppose a symbol X is to be transmitted, and it is transmitted through channel H, and signal suffers noise, which is represented by n, and finally we receive the signal y. So in signal flow, how we can represent this in equation? This is y is equal to x into h plus n, where x is the symbol that was needed to be transmitted, h is the fading channel coefficient, which is a complex variable, and also n, which is the noise. Here h is basically the fading coefficient, and h and n both are random in nature. This we have discussed. Now, the basic figure of merit for analyzing any communication system is the signal to noise ratio. Even if it is digital communication systems, we first of all compute SNR and then talk about how bit error rate can be connected to the signal to noise ratio. What is SNR? SNR is basically signal power upon noise power, which is generally in analysis denoted by gamma. So how do we calculate that for our given equation? Our given equation is y is equal to x into h plus n. In this portion, x into h is basically the signal portion, but this signal is not only signal, it is also under fading, which means it is affected by multiplication of h. Also, there is the signal power that can be calculated, therefore, is the expected value of mod x square into mod h square. So we have to understand that these are voltages. The power will be given in terms of uh, voltage square, v square upon r. Apart from that, also this x is generated using BPSK, which is random in nature. So BPSK symbols, if they are multiple in nature, will take the expectation of mod x square, and also mod h square is the power of the fading channel. So these both constitute what will be the green representation represents, that is the signal power in SNR computation. What is the noise power? The noise power is simply the additive white Gaussian noise factor, and this can be computed in terms of its variance. And again, a statistical representation, it's not deterministic. We treat it as a normal distribution with mean, suppose 0, and standard deviation of sigma n, which means this variance of sigma n square. So what is my signal to noise ratio? This will represent the noise power, of course. What is the signal to noise ratio? It is signal power upon noise power. This is signal power, and this is the noise power. So it is expected value of uh, expected value of mod x square into mod h square upon sigma n square represents the gamma of the channel. Now this gamma is basically random in nature due to the presence of, you can understand we are also taking the expectation of mod x square, the PSK symbols we will generate randomly in any software, MATLAB or Python. But apart from that, this mod h square is going to be random, stochastic, sigma n square is obviously Gaussian noise and therefore it is random. So this gamma is random. So how do we understand the functionality of gamma? We understand that by using the concept called uh, random variables. So random variable is basically a function. This is very important. What is random variable? Random variable is a function that maps the outcome of a random experiment with real number x's. So suppose there is a random experiment and these triangles are denoting various outcomes of the random experiment. Now the random experiment is one in which all the outcomes are independent of each other and the experiment is exhaustive. Exhaustive means whenever we perform the experiment, there is at least one outcome. So this complete set of all the outcomes is known as sample space, and this is the real number x's. So x, capital X, is basically a function that maps each outcome to a real number. So whatever is an outcome, we will represent that as an number on the real number axis. This is what a random variable is. So we will treat gamma as a random variable. For an example, like function that maps the outcome of the real numbers, which is uh, a random variable. Suppose we take a throw of dice as an example. Throw of dice 1 to 6, the faces of the dice are. And whenever we throw, all the outcomes are going to be independent of each other. Whether one comes or two, they are not dependent on each other. And also, it's going to be exhaustive. Whenever we throw a dice, there will be at least one outcome. So this satisfies both the conditions for this to be a random experiment. We say that there are outcomes which are 1, 2, 3, 4, 5, 6, the numbers on the face of the dice. And suppose there is a random variable x that says that this 1 is mapped onto 1, this 2 is mapped onto 4, this 3 is mapped onto 9, 4, 16, 5, 25, 6, 36. You can understand what is the functional relationship. The functional relationship is I square when I is the face, the number on the face of the dice, then I square is a random variable. This is what a random variable does. So now in our example, there are only 6 outcomes. The complete sample space constitutes of these 6 faces that may arise, and they all will be mapped on the real number axis. If a die gives 1, then 1 square is 1. So representation of this outcome, this just represents that dice has 1 on the face, but the real number value that is mapped to this outcome is 1. Similarly, if a 2 comes, it will be mapped to 4, and similarly 9 and 16, and similarly 25 and 36 for 5 and 6 on the dice face respectively. So now the representation, how we represent the random variables, is that firstly what it is a function. It is a function that is mapping all the outcomes on the a random experiment to real number axis. So capital X is the function, it is the random variable, and the small x is the value that the random variable takes. So small x can be 1, 4, 9, 16, 25, and 36. These are the values that capital X takes. The capital X is the function that maps, and x is the value that the random variable takes. Now, how I can use this to calculate the outage probability of the system? So we do that by using the concept of probability density functions. What is a probability density function? In concise, it is a plot versus of fx versus x, where the area under the curve gives the probability. Since it is the density of probability, understand it, this is density of probability, and therefore the area under the curve represents the density, the probability of the event. So suppose the value x is the x-axis. X means the values that the random variable takes, and small f of x is the PDF. Now, what is the representation? This capital X is the random variable, which is also denoted here. And this capital X is the random variable, the function that is mapping. And the value that the random variable takes is small x, which is on the x-axis of the plot. This is the probability density function. So how can I use this PDF concept to calculate the probability? Is very simple. Suppose I have an fx, which is a plot, and I want to calculate that the random variable takes a value between a and b. These a and b are the small x's, and what is the probability that the random variable x can take a value between a to b? So what I will do from the plot, I will take a value a on the x-axis, and I will measure what is the output, and I will take a value b, and what are the individual outputs. So at A, the function has a value of fx of A. This small x is now replaced by the small a, and similarly at B, this becomes fx of B. Now, what we are interested in finding the value of random variable x lying between A and B. How can I do that? Since it's the probability density function, we can always evaluate the area under the curve to measure all the probabilities. This means that in this case, I will draw these two vertical lines, and now the area under this thing between the two vertical lines under the PDF gives the probability of the event uh, that random variable x lies between small a to small b. How do I calculate area under a curve? That is the operation which is integration. So, which means the probability of a to b of x is basically integration of the probability density function from a to b fx dx. So, if we use a small f, the PDF, we can calculate the probability of the random variables. For our case, it will be signal to noise ratio since it is random. Also, the complete sample space constitutes of all the events that are possible in a random experiment. So what is the probability if I integrate this function from minus infinity to plus infinity? The values of a small x from minus infinity to plus infinity constitute all the possible outcomes, which constitutes the complete sample space. And what is the probability of complete sample space? That is sum of all the probability of outcomes, which is 1. And therefore, this property has also to be satisfied in every case. For this fx to be a genuine PDF, the integration of fx dx should be 1 for all values of x. Also, there is another thing that we use that is called CDF, cumulative distribution function. This is defined as the probability that random variable x is smaller than x. Now understand this. This is different from PDF. This is the probability that the random variable x can take a value smaller than x, and it will be denoted by capital F of x. Again, the suffix x denotes the random variable. The small x denotes the values that the random variable takes, and this capital F is basically the CDF of the system. It is an increasing function. So if I plot fx of x, it will be somewhat increasing function. You can understand since from the definition, the value of x less than x. So as we increase the sample space, the probability will increase. The final value can be 1. The smallest value can be 0. Probability can lie only between 0 to 1. That's the basic. So now if I want to calculate again between 2 points A and B, how will I calculate? So understand this. If on this plot, if we take a value of A and measure the CDF at A, again a value of B and measure what is the CDF there, then how will I calculate what is the probability that the random variable can take between B and A? You can understand this. Capital F of B means that X can take a value less than B, and capital f of xa is the probability that it takes smaller value than a. So what is the probability of x taking a value smaller than a? Capital F x of a. What is the probability of capital X taking a value smaller than or equal to b? This will be capital Fx of b. How will I get my probability? I will get that probability by subtracting the probability that random variable x takes B or smaller from A or smaller. It's very straightforward. So this difference between the two CDFs can bring to me the probability that we calculated using PDF using the integration between A to B. Also, the properties that should satisfy it's a increasing function that's by default. But apart from that, the highest value of CDF is the probability of all the sample space that has to be 1, and the minimum value is 0. So small x of f, small x, if it goes to infinity, the value will be 1. A small x goes to minus infinity, the value will be 0. The smallest value of CDF is 0. The highest value of CDF is 1. And from B to A, we can measure the probability of random variable x taking a value between A to B by subtracting the CDF at B and A respectively. So how will now I use this property? The relation between PDF and CDF is very important for that. We have constituted that probability of A to B using small f of x, which is the PDF, is the integration from A to B f of x. And similarly for CDF, capital F of x is basically from B to A. So how were these two related? Small f, if integrated, gives capital F, or vice versa, if the differentiation of CDF is the PDF. So if I want the cumulative distribution function of capital X, I will integrate the PDF. Now this denotation is very important. It's the small f, which is the PDF, capital X, the random variable. I'm using the independent variable of the integration to be y, and I integrate from minus infinity to x, because capital F of x is that. Capital F of x is the probability that the random variable x can take from minus infinity to x. And how do we calculate the probability using the PDF? By integrating. So I'm integrating from minus infinity to x, the small f, and vice versa. It's true also that the small f can be derived from capital F by differentiating. Now we come to the concept of our signal to noise ratio computation, and we have already developed that the SNR on the wireless communication channel is a random process because it's a ratio of two random variables. The expected value of mod x square, mod h square is the signal power, and sigma n square, the variance, is the AWG and noise power. So this gamma is now to be evaluated to calculate the outage probability. What is the outage probability? Outage is said to take place in a wireless communication channel when the transmitter and receiver cannot communicate with each other. So what is outage? We suggest that there is a threshold SNR value gamma TH, and we measure the probability. What is the probability that gamma is smaller than gamma? That probability that the instantaneous SNR random variable is smaller than gamma TH is said to be the outage probability of the wireless communication system. How can I derive that? The gamma has already been derived, and the expected value of mod x square, mod h square upon sigma n square. This needs to be smaller than gamma TH. So this means that this complete thing is smaller than gamma TH. How I can calculate this? We have already seen that if gamma is treated as a random variable, this is simply the CDF, the CDF computed at gamma TH, because the CDF of gamma, if gamma is the random variable of gamma TH, means all the probability that the gamma takes a value smaller than gamma TH. Also, I can calculate that using the PDF and the small f. In that case, we will integrate from minus infinity to gamma TH, small f gamma of y dy. So either I can use integration and PDF to evaluate the outage probability of a wireless communication channel, or what can do, we can directly evaluate using cumulative distribution function at gamma th. The gamma th is said to be the threshold SNR of the wireless communication channel. So I hope this video has helped you to understand the various concept of outage probability. Thank you, and do like and subscribe, and do contact us for research assistance. Thank you.